I'll be talking through the solution to question 7 on the 2015 paper for Massographics and Virtual Environments. So this question is about Bezier curves, and you're given the definition of a degree n Bezier curve here. T is a parameter in the range 0 to 1. Pi are control points given by x and y coordinates. And BINT are Bernstein polynomials, and these are defined here. Okay, thing to note is that this Ni is not a 2x1 matrix, it is actually the binomial coefficient. So part A, using diagram to help you, explain how points on the quadratic Bezier curve are determined from the three control points. So here's my diagram. So P0, P1 and P2 are my control points. And essentially what happens is Q0 is interpolated on the line between P0 and P1 for a certain value of t, and Q1 is on the line between P1 and P2 for the same value of t. Now, the point on a curve, which I've labelled C, is interpolated between Q0 and Q1 for that value for the parameter t. Okay, part B, write out the Bernstein polynomials for a cubic Bezier, so this means n is equal to 3, and here we have the Bernstein polynomials. So we're going to have 4 of them in total, for I equals 0, 1, 2 and 3, and n is always 3. Okay, so it's just a simple matter of inserting n and I into the Bernstein polynomials, and they come out like this. Okay, hence write out the polynomial for a cubic Bezier. Well, it's your first Bernstein polynomial multiplied by your first control point, second Bernstein polynomial multiplied by the second control point, etc. Quite simple. Write out the matrix M when the cubic Bezier curve is expressed in this matrix equation. Okay, so all we need to do here is we take our cubic Bezier polynomial, and we need the coefficients of P0, P1, P2, and P3 as polynomials in terms of t. So this means if we expand out the coefficients, okay, you can see we have polynomial coefficients here. So P0 is multiplied by a cubic polynomial in t. Okay, so M, if I read across the top row, you can see that's simply the coefficient of t cubed is -1, coefficient of t squared is 3, coefficient of t is -3, and coefficient of, the constant 1 is 1. Okay, the coefficient of P1 is similar, 3, -6 and 3, and that gives us the second row. And we continue, and this gives us the matrix M. Okay, finally, we're given the actual coordinates of 4 control points, and we're asked to calculate the points on the Bezier curve for t equals 0.1 and t equals 0.5. Okay, so what we have is we have our coordinates of our control points, which will be a 2x4 matrix. So each P0, P1, etc. are 2x1s. The column of this matrix here are control points. So they have 2, 1. 5, 4, we've got 5, 4 there. Okay, we've got the matrix M, which we just calculated, and then the third matrix is we have our value of t cubed, our value of t squared, and our t and our 1. So for 0.1, we have t cubed, t squared, t, and 1. Okay, so I've multiplied the first two matrices together. That gives us this 2x4 matrix. So do this matrix multiplication, and we have our coordinates of our point on our Bezier curve corresponding to t equals 0.1. Now for t equals 0.5, I'd have the same two matrices as I've got here, so no point redoing that work. I can just use this matrix. Okay, because t is equal to 0.5, we have t cubed will be 1/8, or 0.125, t squared, t, and 1. And again, simple matrix multiplication gives us the solution.